Every year, thousands of companies fail their SOC2 or ISO 27001 audit for the same reason. Their complaints evidence is stale, manual, and disconnected from what's actually running in production. In this masterclass, we are going to fix that by turning compliance into code. Terraform guardrails, automated evidence pipelines, continuous monitoring, all of it build the way engineers actually build. Let's get into it. Welcome to part one of our compliance engineering and automation masterclass. This is an expert level series. So if you're a security architect, a GRC lead, or DevOps engineer who keeps getting pulled into audit season, this one's for you. Over the next 4 chapters, we are going to move compliance out of spreadsheets and into your pipelines, covering everything from Terraform guardrails to fully automated audit-ready evidence collection across both cloud and on-prem environments. Here's the full roadmap for the series. Part 1, which you're watching now, covers the first 4 chapters, what compliance engineering actually is, how to write compliance as code with Terraform and OPA, how to automate evidence collection, and how to monitor compliance continuously instead of once a year. Part 2 picks up from there, building a unified control framework, prioritizing risk, building dashboards leadership will actually read, and designing environments that are audit ready by default. Bookmark this slide if you want the big picture before we dive in. What is compliance engineering and automation? Let's start with chapter 1. We are going to reframe compliance entirely from something you scramble to prove once a year into something your systems verify continuously on their own. Two column comparisons. This is the core mindset shift of the whole series. On the left is how most organizations still do compliance: an annual audit, a folder full of screenshots, policies that live in a document but never ever actually enforced anywhere, and a GRC team working in isolation from engineering. On the right is compliance engineering. Controls are written as code, enforced automatically in your pipelines and at runtime. Evidence is pulled by API instead of screenshotted by hand. And compliance state is true right now, not just on the day the auditor shows up. That's the transformation we're building towards in this series. Before we go further, 4 terms you need to know cold because we'll use them constantly: compliance as code, encoding requirements directly into your infrastructure code, and CI/CD pipeline so violations simply can't ship. Continuous compliance, checking your control state constantly, not once a year. Unified control framework, one master control library mapped to ISO 27001, SOC 2, PCI DSS, and NIST CSF frameworks at the same time. So one control satisfies 4 frameworks. An automated evidence collection, pulling configs, logs, and findings straight from source systems by API, tagged to a control ID. No more manual screenshots. Keep these 4 in your back pocket. We'll build on all of them. The compliance engineering architecture. This is the architecture that ties the whole series together, so take a moment with it. Business requirements, your regulatory and contractual obligations, flow down into controls in your unified control library. Those controls get technically implemented in Terraform, OPA, and Ansible. That implementation is continuously monitored by tools like AWS, Azure Policy, and CM. And that monitoring automatically produces evidence ready for audit. Every chapter from here on is really zooming into one stage of this pipeline, and each stage is engineered and automated, not manual. Real world scenario 1, cloud native SaaS startup preparing for SOC 2. Let's ground this in real scenario. A B2B SaaS startup needs to pass SOC2 Type 2 in 6 months with no dedicated compliance hire. Here's how they pull it off. Every piece of infrastructure is defined in Terraform with zero manual console changes. OPA policies block any pull requests that create an unencrypted or publicly exposed resource. AWS configuration and security hub continuously score their CC6 and CC7 controls in the background, and evidence exports every single night already tagged to the right SOC 2 trust service criteria. Notice what's missing here: nobody's taking screenshots. Real world scenario 2, Regional bank aligning to ISO 27001 on legacy infrastructure. Now, the other end of the spectrum, a regional bank running a hybrid estate of on-prem Windows and Linux servers working towards ISO 27001 certification with no cloud migration on the table. They enforce CIS baselines through Ansible playbooks and PowerShell DSC. Their Splunk CM runs saved searches mapped directly to NXA control IDs. Scheduled scripts approximate continuous monitoring even on legacy hosts, and evidence gets packaged per control into a repository the external auditor can walk through directly. The lesson here, you don't need the cloud to do this. The same compliance engineering principles apply on-prem, just with different tooling. Chapter 2, Compliance as Code. This is where we actually get hands-on with Terraform, Open Policy Agent, and CI/CD guardrails. We'll cover the pattern for both cloud and on-prem environments. The compliance as code loop. Every compliance as code control follows the same four-step loop. First, define, write the requirement in plain language and give it a control ID. For example, S3 buckets must be encrypted and private. Second, implement, encode that in Terraform or Ansible so the compliance state is the declarative version control default. Third, enforce, write an OPA or conf test policy that programmatically rejects any plan that violates the rule. And fourth, gate, wire that policy check into CI/CD so a non-compliant change physically cannot reach production. Define, implement, enforce, gate. We are about to walk through this loop with a real example. Step by step, enforcing S3 encryption in AWS. Let's apply that loop to a concrete AWS example, enforcing S3 bucket encryption. Step 1, define the requirement and assign a control ID before writing a single line of code. Step 2, implement it in Terraform. Declare the bucket with server-side encryption and a public access block baked in. Step 3, add an OPA or conf test policy, a REGO rule that scans the Terraform plan and denies any bucket missing encryption or public access block. Step 4, integrate that into CI/CD by running conf test as a required check before Terraform apply is ever allowed to run. And notice this one requirement maps to three frameworks at once: ISO 27001, A8.24, SOC 2 CC 6.1, and PCI DSS 3.4. One control, three audits satisfied. Terraform encrypted private S3 bucket main.tf. Here's the actual Terraform. Walk through it with me. We declare the S3 bucket, then attach a server-side encryption configuration that defaults to SSC KMS, meaning it is structurally impossible to write an unencrypted object into this bucket. Then we attach a public access block resource with all four flags set to true, which makes the bucket incapable of ever being made public, even by a future engineer who doesn't know the history here. We tag this whole resource with control ID S3 and ENC01, and that ID is a thread that connects this code all the way to the evidence pipeline in chapter 3. OPA, contest policy, reject non-compliant buckets. Now the enforcement side, the REGO policy that actually blocks a bad deployment. Two deny rules here. One fires if the encryption configuration is missing. The other fires if public ACLs aren't blocked. Contest evaluates this against the Terraform plan output, and if either deny rules fires, the pipeline step returns a non-zero exit code and fails. Notice the failure message embeds the control ID S3ENC01 directly in the error, so the engineer who broke the bill knows exactly which requirement they violated and can self-remediate without ever opening a ticket to the security team. CI/CD guardrail in action. Failing with parsing pipeline. Here's what the guardrail looks like in the real world. Side by side, on the left, pull request 482 tries to ship a bucket named logs raw with no default encryption. Terraform init and plan succeed, but contest catches it. Fails the check and Terraform apply is blocked entirely. This never reaches production. On the right, pull request 483 fixes the encryption config. Contest passes with zero policy violations. Terraform apply succeeds and the evidence export job runs automatically right after. This is the guardrail doing exactly what it's supposed to do, catch the problem at PR time, not during the audit 6 months later. Step by step CIS baseline on Windows servers. Now let's mirror that same compliance as code pattern on Prem. On Windows servers, step 1, write a playbook or DSC configuration, encoding the CIS Windows Server benchmark, password policy, audit policy, SMB version 1 disabled, and so on. Step 2, run it against your target servers with Ansible playbook or a DSC morph. Step 3, capture the run output and compliance report into a timestamped control tagged evidence store. Whether you're on Ansible or native PowerShell DSC, both can run on every commit or on a fixed schedule through a job runner or group policy. Same loop as before, define, implement, enforce, gate, just a different toolchain. Ansible playbook, CIS Windows baseline. Here's the actual playbook. Each task maps to a specific CIS control ID. Disabling SMB version 1 is control 18.3.1. Enforcing a 14 chapter character minimum password is control 1.1.4. Enabling logon audit events is control 17.5.1. That's the exact same tagging discipline we used in the OPA example a few slides ago. The pattern is consistent whether you are on the cloud or on legacy infrastructure. Two things worth calling out. This playbook is idempotent, so running it against an already compliant server produces zero changes and zero drift. And the final task exports a timestamped JSON report straight into the evidence path we are about to build out in Chapter 3. Automated Evidence Collection, Chapter 3. We just build controls that enforce themselves. Now let's build a pipeline that proves it automatically without a single manual screenshot. Why manual screenshots don't scale? Do the math on manual evidence for a second. Hundreds of controls multiplied by multiple frameworks multiplied by quarterly refresh cycles. That's thousands of screenshots and every single one is stale the moment it's taken. Nobody can actually prove it reflects current state. The automated approach flips that entirely. Evidence is pulled straight from the source of truth, your cloud config APIs, your CM, your CMDB on a schedule tagged to a control ID and timestamped. It's reproducible, it's current, and it's audit defensible by construction, not by heroic effort in the week before the audit. Slide 19, AWS config, Security Hub, and CloudTrail as evidence sources. Let's build the AWS evidence pipeline. First, enable AWS config across every account and region so every resource change gets captured. Second, create a config rule for each control, things like CloudTrail enabled or S3 bucket server-side encryption enabled, and map each role one-to-one with a UCF control ID. Third, secure schedule config snapshots and security hub findings to export to S3 as timestamped immutable artifacts. Fourth, tag every resource with its control ID like compliance control equals ISO A 12.4.1. So evidence queries can filter by control automatically. That one tag right there maps directly to ISO 27001's logging requirement and SOC 2's monitoring criterion. Sample evidence dashboard, AWS config compliance. Here's what that pipeline produces: a live evidence dashboard, 94% of resources compliant across 312 active config rules with 18 open findings. Break it down by domain and you immediately see where the risk is. Encryption at rest and public access controls are both in the high 90s, but network segmentation is sitting at 76%. That's the real power of this approach. You don't wait for an auditor to find that gap. The dashboard refreshes every 24 hours and shows you exactly where to focus while doubling as your audit evidence. Azure Policy plus Monitor plus Log Analytics. Same pattern now on Azure. Assign built-in policies like auditing VMs that don't use managed disk encryption at the management group scope, so coverage is consistent across the whole organization. Where the built-in library doesn't cover something specific to your organization, write a custom policy definition in JSON, then export compliance state and logs through the Policy Insights API and Log Analytics workspace reports. Three services doing the heavy lifting: Azure Policy for assignment and compliance state, Azure Monitor for metrics and alerts, and Log Analytics for centralized logs you can query with KQL. On-prem, CM as the evidence engine, and for on-prem, your CM becomes the evidence engine. Configure log forwarding from every server into a central CM index. Build a saved search map to a specific control, for instance, surfacing failed logon attempts by user and host. Schedule that search to run and export weekly so it produces a reproducible timestamped report every time. Then store that report in your evidence repository tagged to the control ID and reporting period. In this example, the control is login events must be monitored, which maps directly to ISO 27001, A.8.15 and A.8.16. Splunk saved search failed logon report as evidence. Here's that saved search written out. It queries failed logon event code 4625 groups by user, host and time, filters down to anyone with more than 3 failed attempts, tags the row with the control ID and writes it out to a dated CSV. It's scheduled every Monday at 6 a.m. UTC and the output is retained for 400 days, long enough to cover a full audit cycle plus buffer. Below that, you can see the actual scheduled run, 214 users flagged, control ID clearly stamped, owned by SecOps, exported and timestamped straight into the evidence repository. That's a complete audit-ready evidence artifact produced with zero manual effort every single week. Chapter 4, Continuous Compliance Monitoring. Our final chapter for Part 1, Continuous Compliance Monitoring. We have engineered the controls and automated the evidence. And now let's make sure you know the moment something drifts out of compliance. Continuous with point-in-time compliance. Our final chapter for part 1, continuous compliance monitoring. This is the distinction that this whole chapter is built around. Point-in-time compliance is a snapshot for the auditor, taken once or twice a year, and everything that drifts between those snapshots is completely invisible. By the time someone finds the gap, it might have existed for months. Continuous compliance flips that. Native services like AWS Config, Azure Policy, and GCP Security Command Center or schedule jobs on-prem. Evaluate your control state constantly, surfacing drift within minutes or hours, not months. That gap, minutes versus months, is the entire business case for everything we are about to walk through. AWS Security Hub plus CIS Foundation benchmarks. On AWS, continuous monitoring centers on Security Hub enable it across your whole organization to aggregate findings from config, guard duty, inspector, and more in one place. Turn on the CIS AWS Foundation's benchmark, and it immediately starts scoring every account against roughly 60 CIS checks automatically. Security Hub's built-in framework mappings then link each of those checks to the corresponding ISO 27001, SOC 2 or PCI DSS requirement. You don't have to build that mapping yourself, and the summary dashboard gives you one overall score plus a ranked list of your top failing controls across the entire estate. AWS Security Hub, CIS Foundation's compliance view. Here's what the Security Hub view actually looks like. 80% CIS score across 6 linked accounts with 41 active failed checks. And look at that ranked list. Root MFA enabled is sitting at just 67%. And that single number is exactly the kind of gap that a point-in-time audit would miss for months. But that continuous monitoring surfaces immediately refreshed in real time, ready for someone to go fix today. Policy enforced continuous compliance. On Azure, the pattern is policy enforced continuous compliance. Assign, deny, and audit effect policies for the things that matter most. Mandatory resource tagging, storage encryption, and allowed network configuration. Then the compliance blade in Azure Policy shows you a live percentage score per initiative. ISO 27001, NIST SP 853, whichever standard you're tracking, aggregated across every subscription in your tenant, updated continuously. GCP Security Command Center. And on Google Cloud, it's Security Command Center. Activate SCC Premium at the organization level and you get continuous asset discovery plus misconfiguration scanning out of the box. It surfaces things like public storage buckets, overprivileged service accounts, or VMs missing OS login, and shielded VM protections in near real time. And every finding is already mapped to a compliance standard. Approximating continuous compliance on-prem. You don't get a native security command center on-prem, but you can approximate continuous monitoring with three techniques. Schedule scripts, cron jobs, or task scheduler, run compliance checks nightly and push results into your evidence store automatically. Config management tools like Ansible, Puppet, or Chef run in enforcement mode on an interval, actually connecting drift and logging every remediation as evidence. And CM queries rerun on a fixed cadence, so log-based controls are being re-verified continuously rather than just once at audit time. None of this requires a cloud migration, just the discipline to schedule what used to be manual. Part 1 recap and close. Let's recap everything we covered in part 1. Compliance engineering turns policy language into enforced version controlled code. Terraform, OPA, Conftest, and CI/CD guardrails stop non-compliant infrastructure before it even ships. Evidence collection becomes automated, API driven, and control tagged, whether you're pulling from AWS, Azure, or an on-prem CM, and continuous monitoring through Security Hub, Azure Policy, and GCP Security Command Center replaces the once-a-year audit snapshot with a live signal. In part 2, we go further, building your unified control framework, prioritizing your remediation work by actual risk, building dashboards your leadership team will actually read, and designing environments that are audit ready by default. If this was useful, hit subscribe so you don't miss part 2 and drop a comment with framework you're working towards. I'll see you in the next one.